Again, so now we have the pleasure to end this session on storage with Professor Meng Wang, who's going to talk about high-dimensional data analytics using low-dimensional models. Thank you.
Thank you. Okay, a bit introduction about myself. I'm assistant professor at Rensselaer Polytechnic Institute, short as RPI. We are a private research university in New York State in the US. So this work is done mostly by my students who have just recently graduated, 2 graduates and 2 ongoing PhD students, and in collaboration with Professor Joe Chow at RPI as well. So essentially, the takeaway message of this talk is that although nowadays we have a large amounts of data to process, in many engineering applications, those data are highly correlated, and that leads to these so-called low-dimensional structures or low-dimensional models, despite of these despite of this ambient dimension. So these models include, for example, sparse signals, low-rank matrices, or low-dimensional manifolds. So here, what we are trying to show here is that if we can exploit these low-dimensional structures, we can develop fast, model-free algorithms that can, for example, to recover information or to recover the data with provable theoretical guarantees. So for the application here, the data we consider are phasor measurement units, data from phasor measurement units, data from smart meters. Phasor measurement units are installed in North America since 2009. Now we have more than 2,000 units, and these are mostly multi-channel units. So if we install a PMU on a bus, it can measure the phasor measurements of the bus voltage and the line currents of those lines that are incident to that bus. Of course, we can measure frequency as well. The sampling rate is much higher than the conventional scalar measurements. Now the sampling rate we often have is 30 samples per second. And now they are actually generating a large amount of data. Most of them are stored for offline analysis, some very limited incorporation into real-time operations. So one bottleneck is these so-called data quality issues. The data quality issues mainly result from the device malfunction and the communication congestions between these PMUs to the operators. So at the operator, we usually observe a significant percentage of data losses and also bad data. For example, I'll mention later, I think we have some data from New York ISO, and that in some data sets we have about 10% of data loss. And that also applies to other ISOs. For example, in California ISOs, they have like 10 to 17% of data issues. So that's for smart meter PMU data. For smart meter data, they are actually recently installed in the power system in distribution networks, because 90% of the events outages are actually routed in distribution networks, but conventional SCADA measurements are only available at the substations. Now with these smart meters, we can actually directly measure the consumptions of the customers. So the question we want to address here is that how we are going to use these low-dimensional structures to extract this information from PMU data and smart meter data. So here is one simple example to illustrate this so-called low-dimensional structure of this PMU data. So here we have 6 PMUs installed in central New York. These are like simple diagram here. These are multi-channel PMUs. So they give us 37 voltage current phasors in total. So this is one example of a disturbance. That's current magnitudes across 20 seconds, and you can see the event here. And clearly you can see a strong correlation, because the network in New York is actually very tightly connected. Now if we want to process this data, and we can collect them into a matrix. So this matrix has dimensions 37 by 600. 37 is number of channels. 600 is the number of samples we get in one channel in that 20 period of time. And then we can compute the singular values. As you could see, most of them are very close to 0. You only have a few dominant ones. And that coincides with the illustration you see here. So this is the low rankness of this data. So if I collect the measurements from spatial temporal PMU measurements into a matrix, I can actually approximate them with a low rank matrix. And this low rank property does not need any information about the system topology or system dynamics. You just look at the data and you have this feature. And that has also been used for dimensionality reduction in the recent couple of years. So we are just going to say that, okay, now if we know that the data should have certain kind of low dimensionality, how are we going to exploit this property in our data analytics? So I'm going to talk about two topics here. One is the PMU data recovery. So we have the data quality issues in PMU measurements. We want to recover the missing data. We want to correct the bad measurements. That also include the worst case bad measurements we can get, which are cyber data attacks from the intruders. And another application is for the smart meter measurements. So we want to protect the privacy of these individual users. We want to add certain kind of noise such that you do not identify the pattern of individual users. But at the operator side, we still want to be able to identify what's the load pattern of these individual users. And that's a problem we call data clustering and pattern extraction problem for the operator. So what I'm going to show you is that if we can explore this low dimensionality, we do not need to know the power system model. We do not need to know the topology. We just look at this data, explore this property. We can have fast algorithms, and then we can also have these analytical guarantees to find ground truths. So let me start with data recovery. So yeah, so this is just an illustration about how bad this data quality could be. So this is the data we actually get from NISO. Voltage magnitude, voltage angle, and frequency. All these vertical lines correspond to missing data. So if there's missing data, they probably will set it to 0 or something else, a fixed constant, and then you can see that. So this is just an illustration of our recovered data. The idea is that, okay, if we have, let's say certain percentage of missing data at the operator side, and then the operator can just run our algorithm as the pre-processing process to recover the data, and then the data can be used to following applications, for example, state estimation or even real-time control. So now if we want to use this low rank property, the problem actually is nicely formulated. So it has a simple structure. Now I have this data. It's a collection of measurements from multiple channels across multiple time instance. I have missing data. Also, we can also incorporate bad data, just say missing data for now. The only assumption I need to make is that this matrix is low rank. I don't want to use other topology information. And then if you formulate this in this way, it is a low rank matrix completion problem, which has been studied in the past, let's say 10 years. Motivated by this collaborative filtering problem. So essentially it says for matrices, it can be a rating matrix in this application or other matrices like images or videos. If you have this low rank property, you can actually use the low rank property directly to recover the missing points. So one natural way to look at this is, okay, the only information I know is low rank, so I'm going to solve optimization problem. Constraints are that I should be consistent with my observations, and the goal is to find a matrix that has the minimum rank. And of course, it's a difficult problem. It's actually NP card. So about 10 years ago, the idea is to relax the objective function. So instead of minimize the rank of the matrix, I can minimize the nuclear norm, which is the sum of the singular values. It is actually relaxation of the rank of the matrix. So nice thing about this one is it's a convex problem. You can actually solve it efficiently. And also nice property is that even though it's a relaxation, it can give you the ground truth low rank matrix. So that actually motivates a lot of research on low rank matrix completion in the past couple of years. Now, so what we did in probably 4 years ago is that we make the first connection between the PMU data analysis with this low rank matrix theory. So what we showed earlier is that we can develop methods that use this low rank property of this PMU data matrix to recover the missing data to correct bad data. And this is just one example here. For example, these are all these missing points in one channel. And this is the recovered data from, I think, different variations of our approaches. The nice thing here is that there is a capacity switching event here that's not observed in this channel. But using this low rank model, you actually naturally use this information from other channels to recover the information you need in this particular channel. So all these are very nice, but there's some limitations. So first of all, let me still emphasize the advantages of low rank approaches. they are model free. So essentially, you only look at the data, you assume it's low rank, and then you're done. And you also have the analytical guarantees. Under very mild assumptions, you know for sure you are going to, your solution to your the optimization problem is the ground truth you want to recover. And you can also tolerate a significant percentage of missing data and bad data. So these are all nice features we want to keep, but there are some problems we want to address when we use these so-called low-rank approaches. So most significant one is that this low-rank model does not model the temporal dynamics. So for example, in this matrix, I put the data from each column is the data I get as a one-time instance across all the channels, and these are time from 1 to t. It's a low-rank matrix, we have already verified that, but if I just say permute some columns, I just say randomly switch the order of these columns, I will get a matrix with the same rank, because commutation does not change your rank of the matrix, it's still low rank. But if I look at the measurement at this row, they are no longer a time series anymore, because after this permutation, I have distorted the time. But low rank matrix assumption does not capture these temporal dynamics. So the question that also leads to the bad outcome, for example, if I lose measurements in one column simultaneously, that means I have no observation at all for all the channels at a certain time, there's no way I can recover it. I can use low rank matrix to determine the subspace, but I have no idea where it should lie on the subspace. And if you think about it, you really need some temporal correlation from your previous observations or even future samples to figure out your observation at that time. But this low rank property does not capture that. And another limitation is that if you are dealing with large matrices, you can run convex optimization. Actually, in this case, it's a semi-definite programming. There's some recent work to speed up this process, but in general, it's still pretty expensive. And there's a recent work on how to solve this matrix recovery problem more efficiently. So this is just, before I talk about the approach, let me just show you some example of this simultaneous and consecutive data loss we observe. So this is the data we get antigen is in US. So this is 1 hour. In that 1 hour, all the measurements in all these 3 phases are lost. We have no observation at all. So you really need some kind of temporal correlation to fill that data in. So here is our recent contribution. So what we can show here is that we still have, we can still formulate a simple low-dimensional model to characterize the dynamics of power system. So that means we still do not need any model parameters of the power system that can resolve all these issues of unreliable parameters of the model. And the nice thing is we also have this fast algorithm, the gradient type of algorithm, and we can show that it can converge to the global minimum of this optimization problem I formulated, the matrix recovery problem. And it turns out to be a non-convex problem. But for this particular case, even for its non-convex problem, we can actually find the global minimum very efficiently. And we can also recover simultaneous data loss and consecutive data loss, and also correct errors. So this is the major actually idea. So this is the original data matrix. If you again, this is measurement at one time across all channels, time series in one channel. What we are going to do is just enlarge this matrix, build a Hanker matrix. Hanker matrix in each column. Now you have all the measurements from all the channels for kappa time instance. So this is your measurement vector at y1, y2 to y kappa. So originally you only have this first block. Now you enlarge it to a longer block. You have kappa blocks of measurement here. So the nice thing about this Hanker matrix is that if your data is indeed from a dynamical system, you can show that this matrix is approximately low rank, and the rank is determined by your the order of this dynamical system. Although for power system you have it's a very large, complicated dynamical system. The order is large, but after each individual disturbances, you can always approximate it by a reduced order system. So therefore, the rank of this matrix is also very small. Let me just illustrate these low rank properties through an example. Still, this is a data set we get from Central New York. This is just show some voltage magnitude. The left figure is the approximation error of low rank matrices to the Hanker matrix I built, and this each line corresponds to a different kappa. Kappa is the number of blocks I keep in each column. What I can show here is that this is the approximate rank, and this is approximation error. So even if you say pick kappa equal to 5 or 8, you can still approximate it with a relatively small rank matrix with a very small error. And the rank is much smaller than the dimension of this matrix. To further illustrate that, I permute the time. Okay, for the time series, I just randomly switch the time, and then I build a Hankel matrix. Now you kind of see the low rank property does not hold anymore. Now the approximation error becomes much larger, because if you are dealing with if you're not dealing with these time series measurements, this low rank Hankel property does not exist. Okay, now after we observe this low rank Hankel property, the problem is actually straightforward to formulate. It may not be easy to solve, but it's easy to describe. I want to recover the data. Suppose I only have missing data. Let's not worry about bad data. I observe this is my set location of the observed entries, and I have a missing data. What I want to do is to, okay, I want to estimate matrix X such that they are consistent with my observations at this observation set as close as possible in true norm. So this part is convex. The non-convex part comes from the constraint. I have a constraint that my Hankel matrix of this data matrix should be low rank. Suppose I know the rank R. Okay. It's non-convex, but we have gradient type of algorithm to solve that. So essentially, the nice thing about this algorithm is that we can use these partial observations to find the initial point of my estimation such that it's in the basin of attraction of global minimum. So therefore, although it's non-convex, starting from that initialization, you can actually converge to the global minimum using gradient type of algorithms. So initialization is also easy. You start with your partial observations, you set unobserved ones to 0, you essentially threshold it to a low rank Hankel matrix, and you are done. In each iteration, you move along the gradient direction first, and then here we add this heavy ball step, which is accelerated gradient descent approach. That essentially carries out your update from the previous step, which is known to speed up the gradient type of algorithm. And then you project it to a low rank Hankel matrix at the end of each iteration, then you just repeat this whole process. Very efficient because you do not need to compute the second order information. So this is the theoretical results. So essentially what we can show here is that if you have sufficient number of observations, this algorithm will give you the ground truth low rank Hankel matrix. And the convergence rate is linear, so the algorithm will converge linearly, which means if you set the error to be epsilon, it will be in the order of log 1 over epsilon. And the number of observations you need is very small. I actually need to emphasize that. Remember, suppose your dimension of this matrix is n by n. That means you have n square entries to estimate. If you use the property that the matrix is low rank, so say rank R, the traditional result in low rank matrix completion gives you that you need order of nr log n square measurements. Essentially, that you reduce from n squared to n if rank is a constant, and you ignore log n. Okay. Now, if you further explore the property that it's a dynamical system, you can actually reduce the measurement order to r squared log n. So it's not even linear in n anymore. So that means you can tolerate a significant percentage of missing data. And then we also show that we add this heavy ball step. We show that if you have these, like you tune your parameters of this heavy ball component, you can also speed up the rate. So the rate of the linear convergence can be also further reduced. So accelerated gradient descent is well known to speed up the convergence, but in this setup of this non-convex problem, we actually have the first guarantee to show the analytical, to show the improvement in terms of the convergence rate. And the computational complexity per iteration is low. It's linear in the matrix size multiplies the rank and a log n. Okay. Also, our motivation, we can address this simultaneous data loss now, because essentially you capture the temporal dynamics so that you can fill in measurements across all channels even for some time. So this is just numerical results. We try different patterns of data loss, random location, random time, but correlated location and correlated location and time. And we compared our approach with different kind of algorithm that use a low rank property. The nice thing is in all these cases, our approach is always achieve the smallest error here. And we can also look at this number of iterations in terms of data loss percentage. It's like, for 30% of data loss, we only need about 10 iterations, less than 10 iterations to converge. And also the heavy ball step can improve the convergence as well. So next we move on to the bad data. So for bad data, we are actually considering worst case bad data. So we assume, for example, if you have some cyber intruders, you can actually maliciously change the measurements across multiple PMUs simultaneously. And you can choose those values like carefully such that they will pass your, let's say, bad data detector. So in this case, how are we going to detect the bad data? So in this case, we make no assumption on the bad data except that it's sparse. We just assume you can only change this S number of measurements, but you can do whatever you want to change these bad measurements, and we still want to be able to recover, detect this bad data and correct them. And also we still tolerate missing data, so have a sampling set here. So still, if you want to recover it, it's still a non-convex problem, but easy to describe. I want to estimate my data matrix. I want to estimate my error, and I want to make sure that they are consistent with my partial observations in my sampling set. And this part is convex, but these rank constraint and sparsity constraints are non-convex. Still, we can use this gradient type of algorithm to solve that. So it's like minor change to the missing data algorithm. Now we just need to further handle the bad data. So the idea is that you have a threshold step in each iteration. So essentially, we are going to gradually remove the bad data. We want to first remove the bad data that has magnitude close to my largest singular value of the matrix, and then I move on to correct bad data that are close to my second largest singular values, and so on and so forth. But essentially, each iteration, you first threshold to get some bad data, to get rid of some bad data, treat them as missing data, and then you still go along the gradient direction projected to a low-rank Hanker matrix, and then repeat the whole process. Still, what we can show here is that although non-convex problem, you can actually converge to the global minimum, again, linearly in this case. So still linear convergence rate in log 1 over epsilon iterations. Now the number of, now you can tolerate a significant portion of bad data. So here the torsion we can tolerate is like 1 over R. If you think of R as a constant, which essentially says you can tolerate a constant fraction of bad data at arbitrary locations. And they can be like cyber data attacks. You can correct them, you can correct these measurements. And the sampling, we assume, I should mention, we should assume the sampling is random. So the location of this bad data can be arbitrary, but the locations of the observed entries are randomly selected. So under this assumption, we have we only need like R cube log and square measurements. It's slightly larger than the missing data case because we first also need to handle the bad data. But still, it's much less than this. I didn't mention here. It's still much less than the dimension of the matrix, and much less than this the conventional result in low-rank matrix completion. And in this case, you can just handle simultaneous data loss and corruptions across all channels, even for some time. So this is some numerical examples. We just add some bad data. We also add actually very significant bad data. They are bad data across all channels consecutively for some time. But what we could show here is that if you use our approach, we also have multiple versions. We have this block processing approach. We have online algorithm. But even for online algorithm, you can correct this bad data but still maintain the event. So the reason I want to emphasize that is because if you do not impose any assumption on the, you use any property of the system topology or dynamics, if you only look at the data, bad data and event may be similar because they both lead to significant deviation from measurements before. But by using this low-rank Hanker property, you can capture these dynamics, but these bad data do not have these dynamics anymore. That means you can actually differentiate them just using this simple property online. Okay. So at the end of this the first part, I still want to briefly mention that this low-rank Hanker property actually exists for other data sets as well. As you could imagine, it's a very general assumption. So as long as your signal can be viewed as a sum of a few sinusoids, let's say a sum of R sinusoids, then the low-rank Hanker Hanker matrix should be rank R. So these sinusoids can be damped or undamped sinusoids. So that means you can find these signals in array signal processing, and also MRI, which also have the property that signal can be transformed to sum of R sinusoids, and also video in painting and other dynamical systems. So essentially what we could show here is that all these approaches, they consider these, we call it single channel low-rank Hanker matrix, which means your signal, you have one signal, it can be complicated signal, it can be n-dimensional signal, but it is a sum of R sinusoids. Now we are actually dealing with multiple signals. They are the sum of same set of sinusoids, but with different coefficients. So that in our case is that in each channel, the time series we get is a sum of R sinusoids of the system response, but we have different coefficients in different channels. The idea is that by using this correlation among channels, you can actually further improve the data recovery. Okay. So this is one application for, this is essentially data quality improvement. You can actually use the low-rank, low-dimensional models. Another example is for data privacy enhancement. You can still use these low-rank, low-dimensional models to enhance privacy without sacrificing accuracy. So this is a bit of a motivation. So I think in the early part of this workshop, we mentioned about non-intrusive node monitoring. So essentially the idea is that if you have the power profile of individual household, you can actually figure out the on and off pattern of individual components. For example, you can know when it's a TV or it's oven or something else. Therefore, you can actually figure out the user pattern. So that leads to some privacy concern of the users. That's for smart meter data. And similarly for PMU data, now the data are shared by different utilities, and they are not shared unless under special conditions. So there's also concern about how you are going to protect the privacy of these PMU data. Now, the idea of increasing privacy can be easily achieved. For example, you just need to add noise. Very simple idea. You add noise to you can add noise to the measurements. That noise can be achieved through the sum signal processing approach in the smart meters, or you can just connect a capacitor to each household, and then capacitor can add some noise to the aggregate consumption so that you don't know the pattern. But the question is, if you do that, that leads to inaccurate information for the operator. That means the message you get from the smart meter is not the actual power consumption of the load. So but the operator still needs to figure out, for example, the load patterns, right? So how are we going to achieve that? So essentially what I'm going to show here is that if you use these low-dimensional models of this data, we could actually develop a method for the operator to recover the information from these noisy measurements, in the sense that you can protect user privacy, but at the operator side, we can still get the information accurately. So what information accuracy? So first I need to define what I mean by information recovery. So in this particular application, I'm looking at data clustering and pattern extraction. So what the operator needs to do is that it has the smart meter measurements, for example, from many users, many households. All these measurements may be corrupted with, not corrupted, they have added noise to hide the user information. For the operator, it needs to divide these users into different groups depending on their different patterns. And then for each group, it should be able to identify the dominant pattern of these user profiles, such that, for example, in demand response, it can send the right signal, right pulse signal to that particular group of customers. And you can also use these clustering results to identify anomaly behavior in the system. So if I add noise to my data to protect user privacy, can we still get accurate information for the operator? So this is the, let me first start with the traditional clustering. So clustering is actually a fundamental problem in machine learning. There are many ways to cluster them depending on how you define the similarities of data points. So here we have assumption of union of subspaces. So if each data point here corresponds to a profile, it's essentially a load profile of one user. It's a time series of these load power consumptions of individual users. What we assume is that if you belong to the same group, you will belong to a low-dimensional subspace in the ambient dimension. So the nice thing about this subspace assumption is that even for data points in the same group, they can be far away from each other in terms, for example, 2 norm. That means if you have you may have load that has very different levels of power consumptions, but they have similar patterns. So if you just directly use the 2 norm to measure the similarity, they may be very far away in the Euclidean space. But under this subspace assumption, they are actually considered in the same group. So that's a nice thing to that's why we use this model to model the similarities of the users. So the question, okay, is if I have all these load profiles, I mean, here we actually do not have that. We have the noisy version of it. But traditional version is that if you know the ground truth data, how are you going to cluster them? So this is a traditional problem, and what it still can be solved by can be achieved by solving a optimization problem. Not simple, but simple to describe, but still difficult to solve. So this is my data matrix. Each column corresponds to a data point I showed in the previous slide. So that means it's a time series measurement of one user, the load profile of one user across time. And this color block corresponds to the different groups. Each group belongs, these points belong to the same group. Now, because they have these, they belong to different subspaces, we can find a matrix C that are coefficient matrix, which essentially says every data point can be written as a linear combination of data points in the same subspace. That's very natural from this subspace representation. Now, the nice thing about this matrix C is that it is sparse, block sparse, because you will only have these non-zero elements for data points that in the same subspace. And for these coefficients cross different groups, there's always zeros. So the subspace clustering problem can be formulated into an estimation problem of this matrix. So it's known in the literature that if you can find such a matrix, if you have the data, you can write it as the data equals to data matrix multiply certain coefficient matrix, and it has this self-expressive preserving property. Then you can actually identify the clusters correctly, and you can just apply a spectral clustering method on the C matrix, and you can estimate it. So the problem now still becomes optimization problem. How are we going to estimate this C matrix? You can use the property that it's sparse, so you have the constraint easy to describe. Data should equal to data multiplied coefficient matrix, and then we want to make it sure it's sparse. You can use the L1 norm to make it convex, or you can start with L0 norm to keep the original format. But still, there are ways to solve this clustering problem. The question we want to address is, okay, now if we do not have the data directly, we have a very low resolution of these measurements. How are we going to do the cluster correctly? So here, this is the structure we propose for the power system. So in each household, these are the actual power consumption across time, the time series I'm dealing with. But the output of the smart meter are highly noisy and quantized measurements. So essentially, what we are trying to propose is, if you have actual data, you can map the power consumption to one of the few quantized levels to hide the user information. And effectively, you can think of the whole process as follows. I have the consumption, I add some noise, then I add some random noise, and I apply quantization. And that random noise can be achieved physically or through signal processing. And then the data is sent to the operator. The operator needs to figure out from this highly quantized data which users have similar pattern and what are the load profile of these users. That also applies to PMU, similar idea. You can apply noise and quantization, and the operator side try to recover the data. So what we can show recently here is that we have this, again, fast algorithm for the operator. We don't need any further information, just look at the data and then use the property that it comes from this low-dimensional model. What we can show is that with this approach, if you have sufficient number of data, for example, for the operator, if you have many users and the time series from all these users, you can actually recover the data and recover the pattern and cluster them accurately. On the other side, if you do not have enough observations, even with our approach, you cannot recover it. So that means for the cyber intruder, if you only have access to a few users, you won't be able to correct the information and do the clustering accurately. In that sense, this approach can provide information for the operator while protecting information for the intruder. So I'm going to skip details about this approach, but essentially, if you model this one, this is the data matrix, actual data you get. You may have some corruptions, bad data in the measurements. You are going to add noise and then apply this quantization threshold so that you can get only, like, say, K level of measurements. You want to be able to recover this data and then cluster them from your quantized measurements for the operator. So essentially, if you only have one group of users, so that's a simple case. If you only have one group of users, you do not need to do clustering. You just need to do data recovery. And that matrix becomes a low-rank matrix again, so you have some literature there. And some recent work on data recovery, either using non-convex or convex approach, whether some have guarantees, some do not. And we also have some recent work there that we can show use a non-convex approach, non-convex algorithm, which means that we have a first algorithm to solve the non-convex formulation directly, but we can actually recover the data accurately. But for multiple subspaces, when you also need to do the clustering of these users, there's no work yet. So the problem is actually constrained maximum likelihood estimation problem. So objective function is convex, it's just a log likelihood function. So I want to estimate the data matrix L and also the corruption matrix E. I want to make sure that they will provide my quantized observations, make sure to maximize this likelihood. I have some constraints. This is the constraint for my clustering. I want to estimate these C coefficients such that if it's sparse, I can apply spectral clustering to do the to cluster them. And I'll promote this sparsity by adding sparsity constraint. It's nonlinear constraint. And I also have some constraint on the magnitude of these power consumptions and the corruptions. The non-sparsity comes from this rank constraint and sparsity constraint, and also this product of these two matrices. So let me first show the theoretical results in terms of this recovery performance, and then I'm going to show you our algorithm. So first we are going to show, okay, suppose we can solve this non-convex optimization problem accurately. What would be the recovery performance? We start with a simple case. If you only have one class of the users, it's just a low-rank matrix, it's the simplest case. What we could show you is that if you look at the recovery error of your data matrix, relative average recovery error is upper bounded by this error square root of R over M. So M is the smaller dimension of your matrix and R is the rank, which essentially says, like I just said, if you have many data points, when M is very large, if you indeed have a low rank matrix, this goes to 0 asymptotically. That means you can, if you have sufficient number of observations, you can recover the original data matrix in this sense. And we can also show that this is otherwise optimal in the sense that for any algorithm, you can always find a case of this low rank matrix and this corruption such that your error will be as at least this order. So in that sense, you can do no better. So this is for the recovery of the one class of users. Now, if you have multiple class of users, the results is like similar. Now, it's the order is in the D over M, where D is the rank of the dimension of each individual group. So it's different from the previous one. If you just directly apply the result on the low rank matrix, the order, this here will be the rank of the matrix, so it could be D multiplies the number of groups. But here, within our approach, you can show that it only depends on the dimension of one subspace. So it can still go to 0, the error goes to 0 asymptotically. And still, it's otherwise optimal. You can always find a case that the error is at least as large. And for clustering part, we can show that the global minimizer can give us the right property such that we can do the right clustering. And then we have an algorithm to solve that. So this is alternative proximal algorithm. What we did is that we put the constraints, these constraints into objective functions, and then we just alternatively update these coefficients. We have this low rank component, we factorize them into two matrices, and then we update this data matrix, error matrix, and this C coefficient matrix, and this was thresholding. But the nice thing about this algorithm is that it will converge to a critical point of this non-convex problem from any initial initialization. So for now, we are just starting with mean value of this quantized value, but it can always go converge to a critical point. And the iteration complexity is low, still in linear in the matrix size multiplies the rank. So let me just show you some numerical experiments. Because if you consider special case that you only have one class, it goes back to the matrix recovery problem, so we can compare with existing ones. So this is our recovery error, and all these are other existing approaches. And I want to mention that for this approach, it's dotted line because you actually need to know the nuclear norm of the matrix. Usually you don't, if you don't have the nuclear norm, you actually get up here. But for our approach, you can significantly reduce the recovery error. A more interesting case is the data on the smart meter. So we use the Irish smart meter data sets that have 5,000 residential customers. So for these data set, we actually don't have the ground truth clustering. So we first just, and also it's very, with all these spikes, it's actually very noisy. It's not exactly low rank matrix. We need to approximate it by a low rank matrix. In this case, we can approximate it by a rank 115 matrix. So this blue curve is the power consumption of one user across time. And this one is the quantized data of our approach. So essentially, you add random noise and apply quantization. That will be the data you get out of smart meter. That will be data that the operator can get. And you can see from here to here, the information is lost. Like these spikes are no longer visible anymore. On the other hand, we have some fake high power consumption here. Now, then we use our approach to recover the data. So this red curve is our recovered pattern. So you can see it kind of gets the trend of the original data, but not exactly. That's because we actually add random noise. And also another reason is that it's not exactly low rank matrix. So that's why here we also compared the recovered data with this low rank approximation to the original data. You can see it's more closer to the low rank component. But still, the nice thing here is that you can actually recover from these like low resolution meter measurements the like overall trend of this load. And then we look at the clustering result. We don't have the ground truth data, so we try to see, okay, first of all, how many groups in this data set. So here we tried different number of groups and then apply the existing subspace clustering method to get the cluster result. What we find is that 4 is the best selection under our criterion. Essentially, for the criterion says you want to be as close as possible to the data points in the same cluster, while be as far away as possible to the data points in other clusters. This index is the higher the better. So here, like 4 will be the best scenario. So in that sense, you can cluster these data sets into 4 groups. Now we add noise and apply quantization, and then try our method to see whether we can get the right cluster from this highly quantized data. So these are the comparison of the trend from this ground truth data and the trend we extracted from these highly low resolution measurements. Not exactly same, but some of them you can actually see it actually follows a trend. We also look at the index. So this is the index cluster index you get from this original data, and this is the index you can get from the quantized measurements, still very close to each other. In comparison, if you use other approaches, for example, you can try data recovery first and then cluster. It's actually not as good as this one, because in our case, we actually consider recover and clustering simultaneously. And also, if you tried other approach, then the clustering index is all worse. Okay. So in summary, what I show here is that the data in power system actually has this strong physical correlation. And you can use this correlation to develop a very simple model in the data to characterize the dynamics. In that sense, you still no longer need the power system dynamics, but you are actually effectively exploring them in your data analytics projects. And by using this, you can have a fast algorithm to solve these non-convex optimization problems, and you can also have the guarantee that you can find the either global minimum or the ground truth data you want. And that's one applications. We also have some other work showing that using this low dimensionality, you can improve the event identification in power system as well. Okay. Okay. Thank you.
Very much. Yes.
So you mentioned the first part of the talk, the general recovery problem is NP hard. Yet you have an algorithm that will, when you initialize, you will always get to the attraction region of the global optimal. Yeah, how do you reconcile these two?
Yeah, that's a good question. So first of all, the problem with formalities is not exactly the same. So essentially, here the nice thing here, the original NP-hard problem says that you want to minimize the rank. Given the constraint of observation, I want to minimize the rank. But what we solve here is that I know the rank. I assume my rank is R. I will give this rank constraint. I want to have this true norm of this objective function. So in that sense, I'm already changed the problem slightly a little bit, but still, for this particular case, using these rank information, we can actually initialize in the global, based on the attraction of global minimum. Yeah.
So does that mean if you get the rank right, then you will recover the ground truth?
Yes.
If you get the rank wrong, then what happens?
If your rank is slightly larger, you probably will still be able to find a good one, but if it's smaller, then probably won't get a good estimate. You get a solution to that problem, but it might not be the ground truth. Yes.
Yes.
Maybe a related question. So for the proximal point method, is the convergence guaranteed to critical point or to global? I mean, the original algorithm, the alternating direction.
Yeah, for that part, convergence is only to critical point. We can also say global minimum yet. Yeah.
Yes, a question about outliers and bad data. So we know that all the L2 norm or things like that will be sensitive to bad data. So the first estimation will be biased by the outliers, so it will be difficult to detect that. So it's not very clear for me why you don't have these problems there.
Oh, you mean if you use true norm, it will be sensitive to bad data, right?
Yes.
So that's why we use one norm, not one norm, sparsity. So yeah, that's a good point. That's why we do not use true norm in this case. So here I actually directly model the bad data. I have assumption that this is my model of bad data. I assume it's sparse, but I don't impose anything on its magnitude. And then I want to show that if the observation can be a sum of my ground truth data plus my bad data. And I want to find the bad data as well. So it's not like saying that in this true norm, I already incorporate this beta component. It's not that I want to minimize X with M observation. I want to minimize distance between my ground truth data plus bad data with my observation.
But in your implementation, when you have the algorithm, I understand that you are starting with no bad data, and then you have an implementation with an algorithm that. But you have an algorithm that you have these two loops, or yes, in this case, what are you starting? You need to start somewhere. So at the beginning, you don't have any outliers. Or when you say update, but the first one was what? 0? No bad data. So.
Okay. Yeah, probably I skipped some steps here. I think initialization, yes, both of them are zeros, but then once you get here, you have this gradient descent. So essentially, you have the observation here, and you essentially in this step, you are going to set x equal to the observation you have. So essentially, your first estimation is the data matrix will be your observations. And then once you get to the next loop, you are going to threshold this magnitude. If it's too high, it be considered best data. You room some of them, and then you go along this direction. And next time, your threshold will be lower, and you remove bad data with a lower magnitude, and you move on with this whole process.
But I'm claiming that this estimation is biased, as it's not possible to detect bad data in case of this reversion. if you know all these robust statistics, you know, yes, we have this problem too. If you put the bad data, then you have a wrong estimation. That it's not possible to detect the bad data.
So you're saying you can confuse noise with bad data or something?
Yeah, or you have a wrong model because you are biased by the bad data. Then it's not possible to detect the bad data.
I don't know what do you mean by biased by bad data.
So if you have a regression, for example,
Okay.
if you have a linear regression, and you have a outlier, then you find the wrong slot.
Right.
And it's not possible to detect bad data.
Right, so that's the exactly point we want to address. So essentially, if you want to do linear regression with some data point that's very far away, you cannot just directly use linear regression. You need to model the case that there might be data points that are very far away. And that's what we are trying to model here. These S, we say we are looking for that may be possible that point that are very far away from the ground truth.
So, so it depends really on the magnitude of that bad data. So if the bad data is very far away, I guess your threshold can take them out. But if they are not that far away, then it bias. If they are all, say, in the same direction, but not that far away, that would bias your estimation. And you can imagine that you have, I don't know, a time varying process, and some of the data tells you I'm going somewhere else, that would bias.
Yeah, that's a good point. If you essentially assume all these bad data very close to a ground truth, then essentially kind of noise. Right. So in that sense, we can only say we can recover something that's close to the noise level, but it will never.
It's not a Gaussian noise. It could introduce.
So you
bias.
have to read something on robust statistics from Hubert or Rousset.
I mean, that's a tricky. If they're far away, that's not a problem.
Yeah, I think my question is related to that one. What happens to your approach if you have a systematic error in one of the PMU? I think this is what we are trying to, right? Like for example, if you divide one of the series by 2, or you sum 10 to one of the series.
Yeah, so we actually consider that for systematic errors in PMUs. What we can show is that for the case you mentioned, we cannot recover it unless you impose in assumption. Because if you only change the magnitude, let's say by a 10 or something, the only way you can check it is that is through this, or you can state estimation or something. You have the constraint that it should be consistent with some observations around, and you can correct that. Otherwise, the whole dynamics in that channel is exactly the dynamics as other channels. There's no way to detect them. The easier case will be if in those channels the dynamics are not the same as other channels, then we can locate those channels. But we cannot, probably we won't be able to recover the ground truth trend unless you have some reference point. Otherwise, that still go back to a scaling problem. We cannot determine the actual scaling.
You need the model.
You need not model, except a reference point. For example, whether it's one PU or whether it's 1.1 PU in this channel or not. I can give you the trend, but I need a like scaling, like how large it is. Right. Yeah.
No more questions?
Yeah, early lunch.
No, still. So the dynamics of the system, even though you don't use the model explicitly, the dynamics of the system is sort of embedded in the data. Then when you do the Hankel structure, the dynamic, in fact, you are exploring dynamics itself. Now, if the system dynamic changes, for example, maybe the topology changes, your algorithm would still be able to detect those changes and recover the ground truth? Or?
So yeah, if something changes, we rely on some other detector then tell us there is a change. And then you can use the more updated information to recover it. But in the worst case, if you do not use that, do not know there's a change, you essentially effectively increase the rank of the matrix. Essentially have the model of the original one and you keep the model of the newer one, and then you try to fit your data under these two models simultaneously. Yeah.
And that wouldn't affect the threshold, because if something changes, say
a lot, and the threshold is very little, it seems that all the new data, you could discard it as outliers.
That's a good point. Yeah, so if the threshold is higher information here, you actually, for the theoretical guarantee, the threshold should be somehow dependent on the singular values of my ground truth data. Yeah, if I don't know that, there's there may be errors. Yes.
Yeah, I was thinking, I mean, in this problem you have sort of one what's it called, channel per household.
For second one, clustering, yes. Oh.
Yeah, I was thinking, but if there were like, say, some other problem, or if there were like, for each sort of type or household, there were several signals, and one of them was completely lost, but the other two were still there. Would it then be possible to recover the data, or?
We actually didn't try this, but we tried for PMU data. For PMU data in one substation, we may have multiple channels that measure the same voltage. Yes, for that, we essentially, if you add this knowledge to the data matrix, they say, okay, I have a constraint that these three channels should be similar or close to each other, then you can do that. If you do not add this constraint, we are just going to treat it as a separate channel. Yeah. But you can definitely incorporate that. It will be simple linear constraint in the objective in the optimization problem. Should be able to address that. Yes.
So if you have a system in the PMU example, if you have a system model, can you plug this in? I mean, there are linear relationships between the variables.
Yes, we actually not for this work. When we consider cyber data attacks, we try that. So you can, if you incorporate this topology model, that can enhance your data recovery performance, even the detection of the cyber data attacks. It's doable, and easily incorporated in the system. Yeah, very good point. Yeah.
So, they are a little tired now, so thank you
Very
very
much.
much.
Okay.